So in this lesson, we're going to begin the introduction to physics, and there are some key terms in here that we're going to use throughout the course. So please make sure you understand the terms that we're talking about, even though this is going to be a very math-like section. Math's going to be quite elementary, fairly basic, and then we'll get into some more algebra in our next lesson. So in this lesson, we're going to look at specific terms or speed, velocity, and acceleration. We'll also include distance and displacement there. So first of all, just a reminder, vectors. Vectors are any quantity that have magnitude or size and direction, while a scalar quantity has magnitude, but it has no direction. There are going to be some of these terms that are vector terms and some terms are scalar terms. You will need to know which ones are which and why. So we're going to begin with distance and displacement. Distance is a scalar term. It's the total distance regardless of direction. So if we look at the image here to the right, we start, the distance is quite long, the overall path. It's like going around a trail. But if we look at the displacement from where they start to where they end, it's much shorter. So distance adds all the directions or adds everything up and ignores any directional signs, whereas displacement is the net vector distance from the start to the finish, and it's always going to have direction. And if we think here, well, this is a little twisted, but we're going towards the left and right. It always get me. We're going towards the right in this direction, and then we turn around and then we come back towards the left. So the directions basically cancel each other out. So when directions cancel each other out, we have what we call displacement. Displacement is what we're going to use in most of our calculations, but distance is a scalar quantity that includes the entire length of the trip regardless. So for example, you leave home, you go to Holland College for the day, you return home. You have driven a distance, but your net displacement is 0 because you are ending where you began. Now, if we just consider the trip from home to Holland College, in that case, your distance and your displacement would likely be the same, and I'm assuming we're following a fairly straight path. For me, it's straight down the hill from the, like I was going to say the top of Summerside, but Summerside doesn't have much of a hill. It's enough of a hill, I notice it when we walk. So my distance and my displacement would be very close to the same, just because it's a single line. Once I return home, my distance is going to be very large, but my displacement would be 0. So just key definitions between the two. We will typically, in most of our calculations, displacement is what we will usually use. We're going to do a lot of vector calculations. Now, in this problem, I guess I've got video here. We'll hide the thumbnail. So what's the distance and displacement represented by the problem in the diagram below? So we have an individual, they've gone half a kilometer from home, then they return home, then they go a kilometer from home, and then they go 1.75 kilometers in the other direction. In this case, our distance is going to be quite large. It excludes direction, so we don't have to worry about any directional signs. We're going to have 0.5 plus 0.5 plus 1 kilometer plus 1.75. And the sum of the distance that they have gone is 3.75 kilometers. And if we follow our sig fig rules, we would say, well, that's approximately 3.8 kilometers. Only because there's 1 decimal place in 2 situations, and then we have 2 decimal places here. Displacement, on the other hand, okay, so if we think about the displacement, displacement's going to include the signs. So let's define right as positive and left as negative. So we go a positive 0.5 plus a negative 0.5 plus a positive 1 plus a negative 1.75. This gives us a total displacement equal to negative 0.75 kilometers. Using sig fig rules of 1 decimal place was approximately 0.8 kilometers. We'll include that negative sign to show that it's in the other direction. All right. So the difference between distance and displacement is displacement includes, I got an inch written here. Sometimes my writing doesn't work out very well. So this always has direction. All right. Another two quantities that we have to compare are speed and velocity. Speed is the rate at which distance changes with time. Because distance is scalar, speed is also scalar, so no direction. So we're just looking at, so if I've driven, you're on a trip, or let's say we're just going around a track, and I'm ignoring the fact that I've changed directions multiple times. Our average speed is just the total distance of the trip divided by the total amount of time it takes. Now, speed is much more useful for us in day-to-day activities. I tell somebody, oh, well, it takes about 45 minutes to get to Charlottetown, and based on different towns, speed limits, you probably average about 80 kilometers an hour. We can predict, okay, if it's about the same to go to Surrey, I can say, well, okay, it's this many kilometers to go to Surrey is probably going to take you about this long. And we can ignore the speed part. We can ignore the direction part. We don't have to worry about that. We just kind of get an average speed. But okay, about how fast is my car going? Because your speedometer doesn't give you direction. Now, in physics terms, when we do calculations, we typically will use velocity because we want to consider direction, especially when we get dealing with acceleration. Sorry, I've got a frog in my throat here. So, well, what is velocity? Velocity is the vector quantity, and it's the rate at which displacement, notice we're going to use a vector quantity, changes with time. Okay, time is always scalar because time never has direction. It's always going to include direction, so you want to think about positive and negative signs. Now, the units for speed are always going to be meters per second. You could have kilometers per hour. When we calculate, we're always going to use meters per second for especially any questions that we do in the next lesson where we get into more complex questions. But meters per second is the base unit, and I would advise you to give velocities in meters per second for all of our calculations. Now, how do we calculate velocity? So velocity is the change in distance. Another way to write that is delta D, change in distance, change in displacement over delta T. That delta just means change, so that you'll often see that written, and I'll often shortcut it that way. It just means the final, the finish location, distance, minus the starting displacement. So that's the change in displacement. And this is the final time minus the initial time. Oftentimes you'll see this written as velocity is equal to, so oftentimes we don't necessarily know, we don't need to worry about starting and initial times. We just know how long it's taken overall. So this would be our change, T. And sometimes you'll see it written as D final minus D initial, using little symbols like that. This 0 is, we call it D naught. And technically what that stands for is displacement at time 0. You could use exactly the same equation to calculate speed. You would just use distance instead of displacement, and you wouldn't have to worry about the signs on them. All right, so speed is scalar, velocity is vector. We will use this most. Okay, definitely end up using that most. Your question context will help you know whether you have to consider direction or not. All right, quick question. A car travels around a corner at a constant speed. So maybe we're going 180, 200 kilometers per hour. If its speed is constant, is its velocity also constant? So if its speed isn't changing, does that mean its velocity is changing? Or is it possible for speed to be constant and velocity change? I want you to think carefully about the difference between speed and velocity. There's one key piece that makes the difference between the two, and that should allow you to answer this question. I want you to give your answer and reasoning in the discussion forum. I'm not going to give you the answer here, but I will do some responding there. So I'd love it if you would contribute to that. All right, some example calculations. Example calculations with speed and velocity are pretty straightforward. In the summer of 1988, Summer Olympics, Florence Griffith Joyner won the 100-meter race in a time of 10.54 seconds, assuming the distance was laid out to the nearest centimeter so that it was actually 100.00 centimeters. So we're just basically doing sig figs. What was her average velocity in meters per second and kilometers per hour? So you may find it helpful to make yourself a cheat sheet so you have all the formulas on a single page. I'm not going to give that to you. I would advise you to make your own simply because the process of doing so will actually help solidify your understanding. So velocity is equal to the change in displacement over the change in time. So the change in time from when she started to when she finished, I'm going to list the terms here, was 10.54 seconds. Okay, so that's the same as her change in time. The distance over which she completed that, or the displacement, is 100 meters. Now we're assuming that this is just a single direction that has been run. So we're going to have 100.00 divided by 10.54. You'll notice meters on the top, seconds on the bottom will give us a unit in meters per second. So velocity is going to equal 9.488 meters per second. 4 sig figs and 5 sig figs. Excuse me. We're going to keep 4 in our answer. So 4 sig figs in our answer. All right, so that's the first part of the question. Her average velocity was 9.488 meters per second. Well, how many kilometers per hour is that? So we'll do our conversion, and conversion's nice and easy. Now, being as you are the wind turbine class, you may know this conversion off by heart because you have to convert wind speeds. But we'll do the conversion at the long way. So we start with 9.488 meters per second. I want to turn it into kilometers per hour. So I need to turn the meters into kilometers. So we're going to multiply it by a conversion factor. Meters is on the top here. So I'm going to put meters on the bottom. There's 1,000 meters in 1 kilometer. You'll notice meters cancel. And then we need to change the seconds. So we're going to use another fraction. For seconds, there are 3,600, so 60 times 60, 3,600 seconds in an hour. So 3,600 goes on the top because we want the seconds to cancel out. And then we're going to put the 1 hour on the bottom. So it's the same as multiplying by 3.6, 3,600 divided by 1,000. And you'll get that she ran 34.13 kilometers per hour. If you're not sure how to do that conversion, let me know, but we're just using 2 conversion factors and we're simply using our units to decide whether we multiply by them or divide by them. Second example, you begin a trip and record the odometer reading. It says 45,545.8 miles. You drove for 35 minutes. At the end of that time, the reading is 45,569.8 miles. What is your average speed in miles per hour? So in this case, we don't have to worry about converting to meters per second because we want our unit in the end in miles per hour. Why do you think the word speed has been used instead of velocity? Speed's been used because we're assuming if you're doing a trip, you're going multiple directions. Because you're going multiple directions, we're going to use the word speed. So that's where that comes from. All right, so we need to know the change in distance, which is going to just be equal to 45,569 minus 45,545.8 gives us a grand total of 24.0 miles. Okay. Time is 35 minutes, which is equal to 35 divided by 60 will give you 0.583 hours. So speed is equal to the change in distance over time, which is 24.0 divided by 0.583. We have miles on top, hours on bottom, so that's going to give us 41 miles per hour. Nothing too complex about those calculations. And a third quick calculation, a high-speed train travels from Paris to Lyons at an average speed of 227 kilometers per hour. If the trip takes 2 hours, how far is it between the two cities? So we know speed is equal to distance divided by time. All right, so let's substitute in. So we have 227 kilometers per hour. Now, why am I keeping kilometers per hour? Well, I've given my time in hours. So as long as I put my time here in hours, I can keep kilometers an hour in my work. Now, the next lesson, we will be switching everything to meters per second. And then we have distance between the cities. Time is 2 hours. To rearrange, multiply by 2 hours on both sides. And the distance between the two cities is equal to 454 kilometers. 3 sig figs everywhere, so we just keep our answer at 3 sig figs. So just some simple rearranging. Those are the most basic questions. This is basically grade 10 science covers this whole section. The last piece that we have for today is acceleration. Acceleration is the rate at which velocity is changing. Generally speaking, if it's positive, velocity is increasing. And I probably should clarify that. If the sign for acceleration, if acceleration and velocity are in the same direction, velocity is increasing. If velocity and acceleration are in opposite directions, then you will have decreasing velocity. And what I mean by that is if your velocity is positive and your acceleration is positive, it's going to be going faster and faster and faster in a positive direction. Let's say you already have a negative velocity, so something's falling, so negative velocity. Gravity, which has a negative acceleration, makes it fall faster the closer it gets to the ground. So this increasing velocity, we could say more positive velocity. Okay, if it's positive, you're going to get a more positive velocity. So if you were originally going in the negative direction and you add a positive velocity to it, what that means is eventually you're going to change directions and you'll end up moving in the positive direction, but your speed would become less negative, eventually hit 0, and then go in the positive direction. If acceleration is negative, your velocity will become more negative. So that means, if you're initially going 15 meters per second and you're accelerating at -1 meter per second, your velocity is going to decrease, which means it's going to become more negative or closer to the negatives. Hopefully that makes sense to you. I think as we do some calculations, you'll get that piece. One of the key pieces for acceleration is usually A. So it's change in velocity divided by change in time. We will often see it written as acceleration is equal to VF minus VI, so final velocity minus initial velocity divided by time. There's a couple different ways it can be written in books. Often we write just the time as t rather than two separate times. But another term you'll see is acceleration due to gravity is a constant. G equals acceleration. There's only one L in acceleration. Let me fix this. So the acceleration due to gravity is G, and it is always equal to -9.81. We're going to use that in our meters per second squared. We're going to see that in our next unit. Now, one of the reasons why we usually will use velocity in meters per second is because acceleration is pretty well always given in meters per second. That's supposed to be a squared, not an S, but we'll just leave it be for this lesson. I'm not going to re-record for that. Meters per second squared is our unit. And because velocity is usually changing over a short time interval, it makes much more sense to give it in meters per second. So typically we'll use meters and seconds for everything else. All right, just a couple of example calculation questions. Should be pretty straightforward for us. A car that is traveling 5 meters per second increases its velocity to 25 meters per second in 8 seconds. What's the acceleration? So we have an initial velocity, so v at time 0 is 5 meters per second. Final velocity is 25 meters per second and a time of 8 seconds. So acceleration is going to be the change in velocity divided by time, which is equal to final minus initial. So 25 minus 5 divided by 8. And I've left the units out. I probably should have kept them in. So we're going to get 20 meters per second divided by 8 seconds gives us a total of 2.5 meters per second squared. I'm not going to deal too much with unit analysis because we don't have time to do that, but meters per second divided by seconds will give us meters per second squared. A second example, a car at rest. If a car is at rest, this means velocity beginning has to be equal to 0 meters per second. So even though there's not a number there, that actually gives us some information. All right, a car at rest accelerates at 2.5 meters per second for 12 seconds. How fast is it going? So we have initial velocity, we have an acceleration of 12. Whoops, that's a time of 12, an acceleration of 2.5, apologies. Acceleration of 2.5 meters per second squared and a time of 12 seconds. You'll notice meters and seconds are the only units I have here, which is good. That's what we want. That means our velocity is going to be in meters per second, and that's what we're looking for. So our equation is acceleration is the final velocity minus the velocity at time 0 divided by the change in time. Substitute in and rearrange. 2.5 meters per second squared is equal to our final velocity minus 0 meters per second divided by 12 seconds. Rearranging, multiplying both sides by 12. They cancel. Velocity minus 0 is just going to leave me with v. V equals 12 times 2.5, which is 30 meters per second. Next question we're going to look at. A car that's traveling 90 kilometers per hour slows down and stops in 8 seconds. What's the acceleration? So we have an initial velocity starting out of 90 kilometers per hour. We have a final velocity that is a stop, which means it's 0 meters per second, kilometers per hour. I'm going to use meters per second because we have our time in seconds, and you know that means we're going back for a conversion. And time is equal to 8 seconds, and our acceleration is what we want to calculate. So we need to convert. We need to get our velocity into meters per second instead of kilometers per hour. Oh, I didn't finish my calculations for this one. So if you remember from the last time, to do that, we're going to go 90 times 1 over 1,000 times 3,600 equals. You can look back to the other example. Oops. Let me just erase here. We're going to write this one out because this is why I always write out my unit, because I flip things around. We're going the other direction this time. We're actually going 2 meters per second instead of 2 kilometers per hour. So you've got to do the reverse. Times, I want kilometers to go to meters, so it's going to be times 1,000 meters per 1 kilometer. Times, we're going to have 3,600 seconds. We want to keep our seconds per 1 hour. Hours cancel, kilometers cancel, and there we go. We have our proper unit. So 90 divided by 3.6 gives us 25 meters per second. So now we can put that into our formula. So acceleration is equal to velocity minus v naught, or t, which is equal to 25 meters per second divided by, it's actually in 0 minus 25 is going to give us negative 25. Probably, let me just write this out the long way, just because I'm not there for you to ask quick questions too. So 0 minus 25 meters per second divided by 8 seconds, which gives us negative 25 meters per second divided by 8 seconds, which gives us an acceleration of negative 3.1. We have one sig fig here, so we'll say negative 3 meters per second squared. A little squished in there. So you'll notice the car was traveling in a positive direction. It's stopping. So we know it's slowing down. So expect negative A. We could have predicted that right from the beginning. And then we have another one. How long would it take for a car that starts at rest and accelerates at 2.8 meters per second to reach a velocity of 80 meters per second? So again, starts at rest. Rest, anytime you see that, is 0 meters per second. So listing our terms, V naught is 0 meters per second. It's increasing in speed. So acceleration is positive, so 2.8 meters per second. Sometimes you'll have to use logic to find out if that acceleration should have a positive sign or a negative sign. And then final velocity is equal to 80, which is insanely fast. I actually think this was meant to be 80 kilometers per hour, but we'll leave it be. And then we have our time is what we're looking for. 80 meters per second, seems like a pretty high speed. Yeah, you can do the conversion on that. That's some pretty fast moving vehicle. We'll leave it be for the moment. So acceleration is equal to velocity minus v naught divided by t, plugging in our information, 2.8 meters per second squared is equal to 80 meters per second minus 0 divided by time. Rearranging that, remember from last term, we can do an easy flip. So time is going to be equal to 80 meters per second divided by 2.8. 80 divided by 2.8 leaves us with 29 seconds. And I did the conversion on time, on speed on that. 80 meters per second is equal to 288 kilometers per hour. So it's not your average Civic, put it that way. And that finishes off our calculations for that section. Hopefully that's pretty straightforward for you. We are going to be using those fundamental terms. So make sure you know what distance, velocity, and acceleration, especially velocity and acceleration. We're going to be dealing with those and how the two of them interact throughout the lesson. Now, normally I would take a class and I would go through what we would do if we were graphing with these, but for the sake of time, I have not included that this year, so we're going to do some more calculations, but we may throw a graph in just simply for the sake of helping you interpret a graphical representation.